Okay, we are live. Hi everyone, and welcome to today's very special event. Thank you for joining us today. I am Andrea Pasqualini, Head of Business Development here at Newtwen, and I am here today with our CEO and Principal Engineer. Hi Francesco, good to see you. Great. So while everyone joins, we can talk a little bit about what we will be discussing today. And the topic we will cover will be on advanced motor control libraries and why we believe it's time to rethink how motor control is managed in electric drives. You should be probably able to see my screen at this point. Great. Yeah. So, first of all, we can start mentioning what we will be discussing today with the agenda. We will start with our mission at Newtwen, what we are building and why. Then we look at why this shift is happening now. After that, we will introduce Twin Fabrica, our real-time digital twin platform. From there, we'll move to the embedded intelligence concept, our control layer built on top of Twin Fabrica's models. And finally, we'll show a demo of the entire workflow, focusing on the concrete eDrive functionalities. So, starting from the mission, at Newtwen, our mission is simple but ambitious. In fact, we want to build the embedded intelligence standard for electrified systems, which in practice means enabling motors, inverters, and any e-system component to operate much, much closer to the real physical limits, safely and without unnecessary conservative margins. In fact, I think that everyone here can agree that this state-of-the-art in control strategies is relying on very stringent safety margins. And we believe the next step, what is coming, is different. It will be based on real-time digital twins and closed-loop control deployed directly on the edge, on the embedded hardware. This will eventually dictate a shift from margin-based control to intelligent-driven performance. Now, maybe we can ask ourselves why now? And the answer is simple. Electrification nowadays is pushing everything to the edge. Power density is increasing, thermal constraints are tighter, and efficiency targets are more demanding than ever. Yet, what is happening is that many systems are still relying on heavy derating and over-sensing just to stay on the safe side. At the same time, embedded computing power has reached a level where real-time multi-physics model can actually run on the microcontroller units. This combination here is changing the game. In fact, performance is no longer just a hardware problem, it's becoming a software-defined advantage. So, this is where Twin Fabrica comes in. For the people here that don't know, Twin Fabrica is our software platform that generates real-time embedded ready digital twins. Starting from CAD geometry with material properties, simulation data, test bench data, Twin Fabrica is able to create high fidelity thermal and multi-physics models designed specifically for real-time execution inside the control architecture. Bear in mind that Twin Fabrica is not an offline simulation tool, it's built for real-time deployment. Now, on top of Twin Fabrica's foundation, we developed the embedded intelligence, or EI. Embedded intelligence combines those real-time models with advanced control strategies. And instead of estimating a few measurable variables and applying safety margin, the system is able to gain a much deeper understanding of internal states, like the junction temperature or any hotspot dynamic, and can control them directly. The embedded intelligence is powered by real-time digital twins and can be seamlessly integrated into the MCU, delivering continuous, sophisticated control throughout its entire life cycle and supporting informed decision making. Then, in the demo part of this webinar that is coming in a second, Francesco will show you how these translate into concrete value for e-drives. We looked at closed-loop junction temperature control, overload performance management, cooling fault handling, mean loss per ampere control, WLTP class 3 efficiency improvements, intelligent motor derating control, and all these, again, is enabled by real-time digital twins running on the edge and generated by Twin Fabrica. Now, with that, I'll hand it over to Francesco, who will guide you through the full workflow from model generation to embedded control library, and show you how this approach can redefine motor control for the next generation of electric drives. Francesco, over to you.
Thank you very much, Andrea, for the introduction. Can you hear me well, right?
Yes, loud and clear.
Great. So let's start. I would say that you have perfectly summarized what embedded intelligence is. So basically, it's a firmware layer that we implement in the microcontroller units of electric drive systems, like in this application example. And it's composed by mainly two, let's say, components. One is formed by real-time running models. And for generates these real-time running models, we will see how Twin Fabrica, so the software engineering platform that we have created and that we deploy to our customers, is used, and how easy it's to create these real-time thermal models. And secondly, let's say, algorithms for decision control making in order to improve the electric drive motor control application. And we will see these in details with the features that we have listed. So I'm starting sharing my screen. And as I said, we can start from Twin Fabrica. So can you see the Twin Fabrica interface? Andrea, can you confirm?
Yes, we can.
Great. Nice. So this is the interface of our software, which basically is meant to transform CAD geometry, like we can see here. This is a power module for traction inverter application, silicon carbide based, into a piece of firmware that at the end will be executed in real time in the microcontroller unit. So what can you do inside Twin Fabrica? We will briefly summarize all the steps that are basically reported here. First, you need to import your geometry, so you're capable of reading CAD file, and also you're capable of meshing your file, so create and generate the mesh of this geometry file in order to perform finite element analysis. Why to perform finite element analysis? Because it's the foundational model, the high fidelity model, that it's the base of our real-time running digital twins. Unfortunately, finite element models, finite element analysis, CFD simulations, let's say whatever, it's the high fidelity model that you can create. Usually it's not deployable inside a microcontroller unit because of memory and because of the computational effort that it requires to solve the partial differential equation related to each node of this mesh. No? We are talking about millions of degrees of freedom usually. So inside Twin Fabrica, you can basically perform a reduction. So you can use our model order reduction library in order to compress the high fidelity degrees of freedom of millions of order, which is finite element based model, into a compressed reduced order model, always physics based and also in a state space form. So with this part of the software, you can, with an easy way, just pressing a few buttons and setting some model order reduction tolerances in terms of error and accuracy respect to the full order model, so to respect to the FEM, you can basically compress your model into a set of 40, 50, 30, depends by the setting that you decide, the differential equation, which must be in this way real-time suitable for embedded application. So you can basically execute a model inside a microcontroller unit without losing the accuracy of a full FEM. But then it's not where we, let's say, stop. We do much more because we also calibrate. So in the calibration procedure, you can import measurements like we can see. So we can basically import a set of tests that I can do in my test lab, for example. So let's have a look of how, in this case, a test was performed using IR camera estimation. So I can basically record the currents, DC voltages, the polydiodes sensors implemented in the body diode, as well as the junction temperature recorded with IR camera. And I can actually see how the measurements behaves during a transients operation if, for example, I change the current level of my inverter, okay, passing from 100 to 600, almost 600, like in this case, I can see the junction temperature recorded with IR camera, which has a variation between 40 and 130, like in this case. So this transient test, in this phase, they are used in order to calibrate, in order to enhance my reduced order model such that it can basically perform a very good accuracy. If we look at, for example, test number 1, like in this case, I can make a comparison after the calibration between my reduced order model and my test bench data, in order to see if the degree of fidelity in the accuracy of the prediction of my reduced order model are sufficient enough for my application. So here I can simulate and I can basically report the test. Let's announce this 1 second. So here you can have a look about the accuracy that you can achieve. If we zoom in a certain test, basically we have 4 signals in this case. Let's zoom here. The dashed line is the model, the continuous line is let's say, better to see like this. You have a clear comparison between the real IR camera measurement and also the dashed line, which is the estimation of the model. You can also perform different tests between the one that has been recorded. Let's see, for example, a ramp, so the classical hill hold motor start, where we can clearly see that in this junction temperature, if we zoom in, we can clearly see the kind of accuracy between an IR camera measurement, measuring also the swing of the temperature when the frequency of the motor is low, and in dashed line you have the estimation of the model. Once you're satisfied with the accuracy obtained during the calibration, so inside Twin Fabrica you can train AI models which basically works for correct the state of the physics-based reduced order model, which is foundational based by FEM models. You can go back and you can export this final model into your platform. So basically, I can decide to export into different formats or into Simulink format, like we will see in a moment, or also in a already C code function, which is plug and play into my firmware library. So let's see the Simulink. We will export the deliverable 6. We can also, for example, export it with some test in order to have the final, I would say, confirmation. If we go here and we select this, Okay, now the software has generated this Simulink file, which basically I can go into my MATLAB, position into this path. Let's clear everything. I can open the Simulink. And here I have the block with my digital twin inside exported. So if I run, I will run the test ramp 4 that I have exported with. Once the Simulink has compiled, I can exactly see the variation of the swings in the points that I have exported and also how fast it is. The input and the output of this Simulink block, of course, they are managed directly by Twin Fabric interface. So for example, I can position, like in this case, multiple sensors, not only 3. I can view them directly from here. So here we have a polydiode, here we have another junction temperature, so I can decide basically which node of the mesh of the finite element model I want to explore. I want to have the estimation of my reduced order model. And also I can set different output and different input, of course, of my model. So I have, let's say, many degrees of freedom to operate. However, let's see now, if we go back to our MATLAB platform, how to use that Simulink model into what I called a virtual test bench. So now we will deep dive together with the functionalities of the embedded intelligence and how to use them on an electric drive application. So until this moment, we have just see how easy and fast is using Twin Fabric in order to create and deploy on Simulink let's say, high fidelity models, also calibrated with real experiments. So here in this block, basically, I can simulate both inverter and electric motor that is under test. And this inverter and electric motor model, as you can see, they are they have a quite good accuracy respect to the real test bench experiments because they have been calibrated using the real test bench experiments. And also now I have my electric drive, I would say, control schematic. Usually it's composed by a slow task controller that could be a speed control or a torque control, independently what is your, let's say, specific application case. And also there is the classical current controller with the speed space vector PWM strategy that you can change. So here there is the classical electric drive schematic. It's not, let's say, the scope of this demo. It's not the core of our technology. The core of our technology is this piece. This piece is the embedded intelligence that Andrea has described before. So basically, it's a control block running usually in the slow task. So 1 millisecond, usually, if we are talking about an electric drive application. And the integration of this block within your motor control architecture, it's very, let's say, seamless. It's very smooth. It's very easy, no? You have some input coming from the sensors, usually the 3-phase currents, the switching frequency, the measured speed by the encoder and the resolver, and so on and so forth. And then here you can basically simulate what the real-time models. And also you have control algorithms that are calculating 3 variables. One is 3 scalar variables. One is the frequency derating, which basically it's a scalar factor that will be connected within your reference switching frequency for your electric drives. And why this is important? It's important for derating purpose. We will see in a moment for the inverter. And then we have other 2 scalar values that we have called EID and EIQ, which basically multiplies the reference of ID and IQ coming from your slow task controller. Why this? This because, of course, it's for regulating once again the current or changing the current point in order to enhance the efficiency of the motor, the rating of the motor, and also the rating of the inverter, controlling the conduction losses. So let's see step by step these points here stated in the previous presentation, and let's start on how to simulate and how to see how the embedded intelligence control layer basically is capable of controlling directly in closed loop the junction temperature of the inverter. So coming from here, we can decide to simulate, so we apply a certain reference speed, and if we press play, now simulation is starting. So what are we looking here? Here we have, we can change the coolant flow, we can change the coolant temperature, the ambient temperature, the switching frequency, the limits for the insulation of the motor, the magnet of the motor prediction, and so on and so forth. We have the calculation of the energy loss during the entire cycle. However, now we are asking for a certain speed, 1000 RPM, like in this case, and the controller is following it. So we have basically our speed control loop that has followed the reference of the speed. And here we can clearly see the 6 junction temperature estimation of our inverter, which for that kind of coolant flow and coolant temperature, they are at 120. Of course, they are increasing because it's increasing the temperature of the coolant and so on and so forth. However, if I change the coolant flow, for example, to 4 liters per minute and to 65 temperature of the inlet, so for a different cooling condition, now if we have a look to our junction temperature estimation, of course it has increased with a certain dynamic, but the embedded intelligence, since it has the maximum junction temperature calculation in real time, it's capable in closed loop control to regulate super fast the current and the switching frequency such that my inverter is running within the operational limit that is 175. However, once I say that it's a closed loop control, it means that if I want to change the maximum temperature operation limit, and maybe I don't feel confident with 175, and I want to go with 150, for example, my controller, it's limiting the maximum junction temperature to the new limit, that is 150. So it's a closed loop control, such that I'm changing the current by means of these two EID and EIQ, which are changing basically the reference for the current control, such that the maximum junction temperature of my inverter is safety regulated within the operational limit that I have set. Of course, what I'm doing, I'm losing the current, so I'm decreasing the torque, of course, of my electric drives, and for this reason, I'm also not following anymore the speed. So if before with that cooling condition I was capable of reaching 1000 RPM, now with the rating, of course, I'm not capable of achieving that speed. If you see that the speed is going down, it's because this motor has, of course, the temperature dependency of the flux, no? And since if I go to the digital twin here and I look at the magnet temperature, of course, it's increasing the magnet temperature, which is the blue line here, the flux is changing. So with the same current that I'm limiting because there is the rating of the inverter, which is acting, I'm not capable of holding that torque, and I'm losing the flux because the magnitude of the temperature, of course, is increasing. So it's a very advanced control architecture. And this is how basically we regulate the current and the switching frequency such that in the operation, so in the nominal condition during the continuous operation, my maximum junction temperature is within the limit that I have set. Now I would like to see with you what does it mean to change from 175 to 150. So in this case, 25 Celsius degree of safety margin, under, of course, a certain cooling condition. What does it mean in terms of torque? Fortunately, with the digital twin, we also have in real time the torque estimation. So here we can clearly see during this transient that we have passed from a torque of almost 470 to a torque of 388. So we have lost more or less 80 Newton meter on 400. So almost 20% of the torque that has been lost. Because of what? Because of just a safety margin imposed in my derating strategy in the junction temperature. Now, in the state of the art, usually you don't have a real-time junction temperature running in your electric drive with high accuracy that like the one that we have created in Twin Fabrica, right? So usually you're using the safety margin of 150. What does it mean? It means that with these electric drives that is capable of estimating properly the junction temperature and most importantly, controlling it directly with a closed loop control, you can safely operate your inverter within the maximum temperature operation limit that is actually stated by the datasheet of the supplier usually. So you can basically increase the nominal torque for whatever different cooling condition you have here. Now let's see the other functionality in the list. So the next one is the overload performance management, or like I like to call it, time limited overrating control, TLO. So let's impose a certain conditions for the cooling, so a certain 6 liters per minute of coolant flow rate and 55 Celsius degree for the temperature of the coolant. Okay. And now let's see for a transient, let's say 15 seconds of acceleration cycle, how does our, let's say, controller behave? Simulation in this moment is very fast because the time it's less. And here you can see that there is the classical TLO. So I'm starting with my electric motor at 0 speed. What does it mean? It means that basically I have continuous current for the first instance, just like on one single switch of the 6. Here with my digital twin, I'm capable of predicting the temperature with accuracy for all the 6 switches. So I'm also confident in the estimation, and this estimation is also confirmed, if you remember, by the IR camera measurements in this simulation. No, it's very similar. This kind of hill hold motor start when the speed starts from 0 and increase with a certain ramp. Now, what I have to do is to basically limit the current such that I fastly regulate the maximum junction temperature within the 175 Celsius degree. So in these, let's say, conditions, now I'm achieving the target speed more or less in 3.17 seconds. Okay. Now, if we go back here and we say, you know what? In my datasheet of my power module, there is also written that I can stay for, let's say, cumulative amount of time, more or less of 100 hours in an overload, in an overrating, in an overheating region. So between 175 and 200. However, in my application, let's say a passenger car, I want to guarantee for my inverter a certain number of cycles, of acceleration cycles during the life of the inverter. So I calculate that if here I say, okay, for a unique acceleration cycle, I can stay no longer than 3 seconds within this overheating region. What does it mean? It means that for more than 3 seconds, I'm allowed to stay with the inverter hotter than the maximum operation limit, which is directly translated into acceleration performance, torque performance, so peak current duration that it's increased. Let's see if it is true. So if we go back here now and we press play, we should see that I achieve the target speed, so the acceleration has been increased because now I achieve 1000 RPM in more or less 2.50, 52, 50, 51 seconds. So I have increased by far the performance of the acceleration from 0 to 1000 RPM for my electric motor. How to do that? Thanks to the TLO. So if we go back here, now my algorithm allows me to stay for 3 seconds within 200, let's say, Celsius degree. And if I go back and I look for the current, in fact, during the first instance, I'm asking for the maximum current, which is 800 amp. So now, this is very important for the overload management, no? Regulating basically how much time I can stay within the limit and regulating the overheat region, I can increase the torque performance, I can increase the acceleration performance of my electric drive, which is one, let's say, relevant KPI for electric motor, mostly in the automotive application. Now, if we go back to our list, performance, of course, matters, but also safety. Safety is the other important KPI, no? So usually one of the, I would say, faults sometimes involve the inverter in an indirect way. What does it mean? It means that usually you can have a fault in the coolant system, maybe the pump, maybe you have a loss in the pipe, whatever. You're not capable of basically guarantee the nominal liter per minute and the nominal inlet temperature for the cooling of your electric motor and mostly of your inverter. So what happens? It happens that you have sometimes NTCs or polydiodes or diodes thermal sensors implemented in your inverter. Of course, the dynamics of this sensor is not in the junction, so it's very, very slow to arrive to, I would say, a dangerous limit. And so it's too late basically to cut off the current and to save the inverter, which has a very fast temperature dynamic, as we have seen. And you need to protect it by a fault that is in the cooling, it's not the inverter. So now, with this virtual test bench, we can also try to replicate this condition. So, for example, with this, let's increase the seconds of the simulation. Now, with this condition, let's start with the standard conditions here. We can see everything is going fine. In theory, my speed has been achieved. Yes. So now, what does it happen? It happens that we can basically increase the temperature of the inlet, and we can also say, okay, instantly, now the coolant flow of my inverter is 0. And see what happens to the electric drive. Here, if we go back to our junction temperature estimation. Of course, when I have increased of 75 Celsius degree the inlet, the temperature has increased as well. However, when I put to 0 the coolant flow, so actually I have simulated a 0 coolant flow, my junction temperature now fastly is controlled to be 100 Celsius degree. Why 100 Celsius degree? Because here is one of the parameters that I've imposed. So the safe junction temperature condition when my embedded intelligence algorithm recognize a fault and recognize a fault very fast, regulate the new reference for the closed loop junction temperature control. And one of the main advantages, control the inverter is safe. It's operating at a very safe junction temperature because I know that there is a coolant fault. Of course, my electric drives cannot perform the reference of the speed because I'm in a fault condition. However, what I'm preserving the continuity of the service because I'm not putting to 0 the current, but I'm regulating in a closed loop control the current reference such that during this condition the inverter operates at 100 Celsius degree, which means if you go to the torque or to the speed that with the same let's say inertial and viscosity load, instead of 1000 RPM I can go to 270, okay, but with the junction temperature that it's safely controlled to 100 Celsius degree. So my inverter is safe, and with this slow temperature I can arrive to I don't know, a station in order to recover my fault in the coolant. So the continuity, the preservation of the service and the enhanced safety thanks to the embedded intelligence control on top of the motor control drives, of course, is one relevant KPI that our digital twin-based control offers. So, going on with our list of features, now, until here we have been focused on the inverter, that of course it's the actuator for controlling the motor. Now we can focus on the motor. And in particular, I will show you the concept of the mean loss per ampere. What does it mean, mean loss per ampere? During the state of the art, and working close with many of our customers, usually in this slow task controller, in order to calculate the ID and the IQ reference frame in order to follow certain torque or a certain speed reference, what does it happen? It happens that sometimes you can implement, of course, lookup tables. In the best cases, they are 4-dimensional lookup tables, where based on the ID, IQ, the speed, and the temperature estimation of the winding and also of the magnet, you can basically calculate which is the MTPA, so the maximum torque per ampere, or the flux weakening point, based if it depends on, let's say, the voltage limit that you have at your disposal. However, these lookup tables, most of the time, they don't have the, let's say, proper resolution. And the other main problem is that they are temperature magnet dependent, and this temperature magnet estimation in real time, most of the time it's not available in the classical electric drives control. Or if it is available, it's not accurate enough. With the digital twin technology, so with the Twin Fabrica, using the same identical workflow that you have seen, you can achieve a real-time thermal model of the electric motor that is also very accurate, not only in estimating the hotspot in the windings, which are useful for the preservation of the insulation class and also for maximization of the rating limits, but also is capable of predicting in real time, as we have seen here, the magnet temperature. Okay, and this real-time variable, it's used within our, let's say, embedded intelligence algorithm in order to modify the state of art. It's completely independent by the kind of motor control strategy you can have here, because working on the reference that you give him, it's basically change them such that it achieves the references that he has calculated. And the references that he has calculated, it's always the maximum efficiency one. So the current point, ID and IQ, that minimize the total losses that you have in the motor. And for some points, mostly for, let's say, relatively low speeds and medium torque, the MTPA point, it's not coinciding with the minimum loss point, because the Joule losses or the Joule losses, they are basically lower than the iron losses and the permanent magnet losses. So with this firmware block here, automatically the algorithm change dynamically, so change in real time, the current operating point such that you maximize the efficiency. So let's see how it works. For example, suppose that you don't have time to implement your lookup tables, you don't have, let's say, enough data, you don't have, let's say, enough memory for very high resolution lookup tables. So sometimes we have seen customers, maybe not the most advanced one, that are controlling an IPM like an SPM. So basically imposing an ED current equal to 0 and leaving the rest to the slow task controller, PI controller, to impose a Q reference current such that you follow the speed or the torque. So for example, for this test, now let's reset properly our temperature inlet and coolant flow. Okay. Now we can enable or disable with one unique parameter our min loss per ampere. And let's start with the MLPA off. So basically, I'm not changing the references here. Let's enlarge a little bit the simulation time. And if we go, here we have our speed reference that is completely followed. And I also have my torque to achieve that speed, which is more or less 524. And now I also have the power loss calculation here. So with that ID and IQ, I have a certain power loss total for the electric motor, total losses for the electric motor. And it's calculated in real time. Of course, it's increasing. Why? Because the winding temperature is increasing and the magnet temperature it's increasing as well in this operating point. So now let's see what happened to my reference currents when here I enable the MLPA. So now that I have enabled the controller, what does it happen? It happens that the speed it's always followed. So I'm always at 1000 RPM. The torque, it's always the same. So I'm asking basically at the same, apart for the, let's say, small transient here, I'm asking for the same torque level, okay? But what has changed? Has changed the current point. So before, without knowing nothing, I was controlling my electric motor with 0 direct current and a certain IQ and a certain quadrature current. But now my embedded intelligence algorithm has changed completely the operating point and has positioned itself fastly in a new point such that it has minimized losses. So let's see if we stop the simulation, what happened to the power loss calculation during that transient. During that transient, my power loss calculation, which of course, I repeat, it's continuing to increase because it's the temperature of the magnet and of the winding that it's increasing, so it's temperature dependent. However, here I have saved a lot of watt hour. a lot of watt in terms of losses, sorry, not watt hour. So in terms of efficiency, if we want to also calculate this, we have saved also the efficiency. It's going down with the temperature that it's increasing. However, here we have saved more or less 2 points of percentage, just changing the reference of the currents, but holding the same speed and the same torque. Now, we can see what happens if we scale this. And this will be, let's change, for example, this to 60. And let's go for 6 or even 8 liters per minute. So the nominal flow rate for the coolant. But now we start a new let's say, profile. So a VLTP class 3. So now we are still controlling everything in speed control, but the reference, it will be a world class, let's say 3 cycle for the drive. Okay, and let's start the simulation without using our mean loss per ampere control. So just the classical, let's say, electric drives, imposing the current equal to 0. Now, if we play, what we will see is that the new reference, of course, is no more a constant, but it is a VLTP class 3 cycle. So you have the urban, extra-urban, and highway cycles during half an hour, more or less. That our control, of course, it's following. We are also imposing some torque load in order to, of course, achieve that that speed. That it's a, let's say, quite realistic torque profile for a VLTP class 3 cycle. And if we have a look to the junction temperatures of our inverter, of course, the inverter is quite cold with this coolant condition, and with the VLTP class 3 cycles, I mean, we are accelerating, decelerating, but we are not racing a Formula One. We're not driving a Formula One race in this case, no? If we have a look, you can see clearly the 6 junction temperatures. You have the accelerations, the swings of the temperature in different profiles, and so on and so forth. So the digital twin can really gives you a quite real-time overview of your electric drive. That's the reason why more insights, it means more control, and more control, it means more performance and safety. However, here it will take a few minutes, of course, because simulation is long and we are performing everything. So there is the electromagnetic motor running, the thermal motor running, electromagnetic and inverter models running, the electric drives with the speed control and the current control algorithms, and also the embedded intelligence, let's say, block that are running in real time on my laptop. That is not super powerful, let's say. Here, repeat, we have all the details. We do not change now in this moment the temperature inlet and the coolant flow, but you can do it. So you can basically simulate these cycles for different cooling conditions, different ambient condition, different temperature condition, different switching frequency, and so on and so forth. However, in this moment, it's not the scope, because we want to calculate the total energy loss, okay, in watt hour, that actually our electric drives it's spending, so the losses, so the total energy losses, in order to perform this VLTP class 3 cycle. So it's not the total energy, but it's the total energy loss. So the losses of the sum of the losses of the electric motor and the inverter. So if we wait a little bit, we will see that at a certain moment this energy loss will stop when the simulation will stop. So after having simulated 1,800 seconds, that is the duration of the VLTP class 3, and this will stop at a certain value. And we will see that if we repeat the same identical test, so with the same cooling condition, with the same speed references and with the same torque load, but using the MLPA control powered by enhanced by the embedded intelligence, so modifying the current references, you will see that you have a very good saving in terms of energy. And this energy saving, actually, the value is directly translated into what? It's directly translated into extension of the range capacity of the vehicle, okay? Or with the same identical range requirements, you can save on the cell. So if the watt hour here, it's considerable enough in order to save 1 or 2 cells in a battery pack, it's a good cost saving in terms of bill of material, because we know that the battery pack, of course, is the most expensive component in a car, in a vehicle, let's say, and the cell it's quite expensive as well. So if we can save a couple of cells, we are saving, let's say, euros in orders of tens, okay, not cents, not cents. So let's also have a look of the temperature winding and the temperature of the magnet. Of course, during a VLTP class 3 cycle of just half an hour, it's normal that I'm not overheating my system. However, later not in the next one, but in the last test, we will also see how the rating for the motor it's quite advanced in terms that it will be a cascade rating that is taking into account simultaneously both the temperature of the winding and the temperature of the magnet, because winding is very relevant for, let's say, safety reason and for the insulation class. But magnet is quite relevant for preserving the efficiency of the electric motor. However, simulation has finished, and the total, let's say, energy loss is 1.1 kilowatt. So let's remember now this number, because we will repeat the entire VLTP class 3 cycle with the same identical speed and torque references, but using now different current let's say, points that are dynamically calculated, also based on the magnet temperature estimation, as well as all the electromagnetic model of the digital twin generated, calibrated, and deployed by Twin Fabrica, remember, in order to calculate at each time instant, and in particular each 1 millisecond, which is the rate of the firmware where this code it's running, the variation on the ID and IQ reference of the standard motor control in order to improve the efficiency of the electric drive in a dynamic way. And in particular, I would like to highlight how this block it's really easy to be implemented, because basically it is a function which inside has the real-time running digital twins that are giving you all the enhanced information about total losses, the torque, the efficiency of the motor, the temperature of the motor winding, the temperature of the magnet, the 6 switches temperature of the inverter, in order to have this information and inside having a closed loop PI controllers, basically, on cascade, on a particular structure, let's say, that are regulating the current reference such that the limits on stator insulation, permanent magnet temperature limit, maximum operating junction temperature for the inverter, the safe junction temperature condition when there is a fault, the maximum temperature limit overall when you are, let's say, in an overload performance that we have previously seen, they are dynamically regulated, completely independent completely independent by the cooling condition. So even if you change the cooling condition, the models can predict quite well the temperature states, okay, and can regulate the electrical variables such that you can directly control them in a safety way, pushing with the so-called state of function. So pushing with the current capacity of my electric drive, which is composed by an inverter that is the actuator of my electric motor. Say that, we can always see the VLTP +3 cycle that is running. So I'm following the speed reference here. We can see the torque generated by the motor. It is completely identical to the one when the MLTPA it's disabled. So when I'm using the standard classical electric drives, so even if I'm basically using my IPM like an SPM, why? Because there is a PI controller that is regulating the torque, but the efficiency, so the losses, we will see that can be improved. Remember that at the end of the cycle, the total loss calculation was 1.1 kilowatt. So let's see, after this half hour of driving cycle, what will be now the new energy loss calculated, only changing the ID and IQ references. So basically only performing the MLPA algorithm that is inside the embedded intelligence. For giving you some practical numbers in terms of memory and in terms of computational effort of this firmware layer, which is encapsulating all the functionalities, all the closed loop controls, and all the digital twin models that are estimated real times, all these variables that usually you don't have with the state of art, let's say hardware sensing inside your electric drive. In an Infineon TC3H7 microcontroller, which is a standard in the automotive space, this code here, it's running in less than 50 microseconds, so quite, let's say, suitable for the 1 millisecond implementation task because it's less than the 5%. And the total memory for this, let's say, functional block here, it's less than 70 kilobyte. So very, very, I would say, light model. That's almost finished. We have the final accelerations here. So simulation is running, and we are saving more or less 90 or 87, whatever, watt hour, 90 watt hour. That for a unique single BLTP class 3 cycle, it's a lot. So basically, it's a very good saving. Why? Because the electric drives is changing the ID and IQ current references in real time in a dynamic way, such that you serve the torque of the load condition in order to achieve the reference speed, of course, but minimizing in the real-time strategy the total losses for the electric motor. Now, to finish, we can set a very, let's say, I would say very high here, very low here. And we can see, if we go back to our state, the final derating. So here we can see how we will manage the, I would say, motor control. So the motor temperature, no? The insulation class, usually it's, the limit is 180, no? For preserving the insulation of the windings. Now we are asking for a very high torque in the electric motor, and it's a continuous operation point. That's the reason why the temperature is increasing in a so, let's say, regular fancy here. And the magnet temperature limit, it's 100 Celsius degree. And we know that the dynamic of the rotor temperature usually it's quite slower than the one of the windings. However, it's very important to predict the magnet temperature because mostly because it's very slower respect to the stator. When I switch off my car, for example, when I park and I go to the food shop for a few minutes and then I restart, maybe my stator is already at a very low temperature, but the rotor is still very hot. So with the on-off, 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 on-off conditions, what does it happen? It happens that the magnet temperature is always starting at a very hotter point, and so it's not so difficult during these conditions, so mostly in the automotive application, that the magnet temperature basically achieve the limit that are jeopardizing, basically that are compromising the efficiency of the motor, because you know that if the motor the rotor magnets, let's say they are overheated, you lose the flux, this loss of flux, it's irreversible. It's an irreversible process, and basically your electric motor with the same current now can give less torque, and that is what basically compromised the remaining useful life of your electric machine. Now, what we are seeing here, we are seeing that the embedded intelligence basically is doing like it was doing to the inverter. So it's regulating the current in order to have less Joule losses in the winding and to hold the maximum available current such that the maximum temperature in the winding is preserved, basically doesn't go above 180. However, even in this operational point, the magnet, of course, has changed. As we can see here, it's dynamic because the current now operating point will be different. But at a certain point, I'm still reaching the, let's say, 100 Celsius degree limit that we have seen here. So these are limits that, of course, the user can change, no? So whatever there is here in terms of parameter, the user can change, and they are automatically set in the library of the firmware. So if you always, if you want to use some safety margin, you can always do that. However, the algorithm, as you can see, first has changed the operational current point, and now it's still changing it, because if we go back to our digital twin temperature, I was reaching 100 Celsius degree, and now the new current operating point, of course, is slowing down such that I do not overheat my magnets. Doing this, it's not an easy task, because the dynamics of this magnet is quite slow, and you need to use a predictive controller inside this in order to, let's say, calculate which is the final steady state current level of ID and IQ, such that I preserve still my operating condition, of course, on a lower speed, because I don't have enough current for my motor, because it's I'm risking the overheating, so for safety reason. But I'm still preserving the continuity of the service, but preserving the life of my electric motor. So even the lifetime of your electric drives using the embedded intelligence algorithm is enhanced, it's improved. That's it. I will stop here with the presentation. We have covered all the points, because you have seen also the VLTP class 3 efficiency announcement. It was the, let's say, slower task to see, because we had to wait half an hour and then another half an hour of simulation of the entire VLTP class in order to, let's say, observe the efficiency preservation, okay, during this cycle. The good thing is that when you try this kind of electric drive architecture, it's very easy. You use Twin Fabrica, you use the embedded intelligence. You integrate just adding these three variables within your motor control, whatever you have, and you can perform the same test that I have performed here in the Simulink in your test bench using on-off MLPA, using different, let's say, safety margins, basically disabling and enabling the embedded intelligence algorithm in order to measure the kind of added value that this piece of firmware adds to your motor control. So we have a question from Peter. What level of visibility does the embedded intelligence model provide, and to what extent is it explainable? What customization capabilities are available? Is it basically black box model? Very nice question. Actually, it's not a black box model, so you can see both firmware at the firmware level and also inside the Simulink. So you can also, let's say, customize it if you want. The level of customization, usually we have a set of modular functions that we offer to our customers. However, these modular functions, they can be chosen or not to be included inside that box. That is not black, it's a white box model. And sometimes we also cooperate with our customers if they have specific, let's say, control functionalities they want to develop that are always, let's say, enhanced by the digital twin, insights in real time. We also cooperate with our customers in order to provide new modules inside the library of the embedded intelligence that they can integrate within their electric drives.
How are these models validated?
Nice question. As I mentioned before, within Twin Fabrica, you use real-time data coming from the real test bench. So most of the time, electric motors and inverters, they are oversensed for special prototypes in R&D labs. So you have temperature of the magnets, multiple temperature in the windings. You can use an IR camera on a black module for the inverter in order to measure directly also the junction temperature. And once you import this real test bench data into Twin Fabrica, you can calibrate the model and also validate the model within Twin Fabrica before to export it in the Simulink environment or within your electric drives application. So the validation phase is always made by real test bench data. At the beginning, you mentioned that the CAD structure of the inverter is used as an input. Besides the CAD data alone, what additional information is required? For example, material properties, electrical characteristics, operating condition, etc., etc. So yeah, inside Twin Fabrica, you can also get a look to our previous seminar where there was one dedicated on inverter digital twin make procedure. And basically, yeah, we start from the data. Inside Twin Fabrica, you set material properties, you set the power loss model using maybe datasheet model, datasheet data, so the classical curves of voltage and current for different junction temperature and for different voltage gate driver. Same for the switching frequency losses. And then, yeah, you can perform the finite element analysis and the reduction inside Twin Fabrica, and you can calibrate this reduced order model with the additional data coming from the test bench. Is the option to generate C code equivalent to generate a Simulink model and then leverage automatic code generation workflow, or the C code is kind of differently optimized to some extent? Okay, the C code is generated by our own compiler. It's quite similar to how the Simulink is generated. However, in the C code, you will find the classical .c and .h files with all the components, basically. You have the source code of the final digital twin, and the embedded intelligence library we have basically an integration user guide for different microcontroller units from Infineon families to ST families, TI, and etc., etc. And the integration is quite seamless, and we have all the documentation to easily, let's say, satisfy this task. For giving you a reference in terms of time, one firmware solution engineers, once it exported the C code from Twin Fabrica and follow the reference guideline for the integration user guide, it takes a couple of hours to finalize the integration within its own, let's say, firmware architecture of the motor control drive. Then we have another question. Can we simulate the inaccuracies in the sensors, like current sensors, temperature sensors, position sensors, to estimate overall inaccuracies within the system? For sure, with Simulink, I repeat, it's not frozen. You can manipulate whatever you want. You can add disturbances in the current sensors. You can add errors or biases in the position, and so on and so forth. So when you are on Simulink, you can basically simulate whatever conditions you want, like I did mostly before when I put to 0 the liter per minute speed of the coolant. I have simulated somehow a fault, and I have basically recorded and seen how the control behaved within against that fault, basically. So how my control strategy has performed within a fault condition. Your model appears to run very fast and smoothly. Does it also include a fast current loop operating at the switching frequency level in the microseconds range? Very nice observation. We didn't simulate, in this case, the PWM. So we didn't simulate the carrier of the PWM, but the fast task of the current control was 100 microseconds. So in the period of the PWM, but we didn't simulate the PWM, so the carrier. Straightly answer your question, 100 microseconds, so 0.1 milliseconds for the fast task of the current control loop. The simulation was very fast also because the digital twins, they are very compressed.
Thank you, Francesco. Thank you
Great.
everyone for joining. Hopefully it was helpful, and looking forward to discussing it in case you'd like to dive deeper in the coming weeks.
Thank you very much, everyone. Bye bye.